Welcome back. During the past 7 lectures, we've been looking at individual structural elements, each standing alone with its own external loads and reactions. But in the real world, very few structures actually work that way. In the buildings, bridges, and towers that surround us, structural elements are almost always components of structural systems, assemblies of multiple interconnected load-carrying elements. There are exceptions, of course. Trajan's column is just a column, and unlike most columns, it supports no other structural elements above it. No architraves, no arches, no trusses. The St. Louis Gateway Arch, it's just an arch, at least when viewed from the outside. But on the inside, there's actually a fairly complex structural system that's used to support the tram or elevator that transports visitors up to the observation deck on top. So maybe it isn't just an arch after all. And that's the point. Standalone structural elements are rare. Virtually all of the world's great structures are structural systems. Our purpose today is to learn how to discern the structural system in a building, bridge, or tower, and then to analyze that system, to understand how it carries load. The typical dictionary definition of the verb analyze is to examine methodically by separating into parts and studying the parts' interrelationships. And that's exactly what we're going to do here. To analyze a structural system, we're going to take it apart in our mind's eye using a methodical sequence, starting at the places where the external loads are applied, and then continuing from element to element, following the transmission of forces all the way down to the structural foundations. Along the way, we'll be focusing on the connections between those elements, because these are the locations where the force is transmitted from one element to the next. This chain of elements and connections is commonly called a load path. And understanding load paths is the key to understanding structural systems. Now, as I said, analyzing a structural system involves taking a structure apart in our mind's eye. You can't see inside my mind, so let's try using a model to illustrate how this process works. And I'd like to use a model of one of my all-time favorite buildings, the beautiful church of San Miniato al Monte in Florence, Italy. So let's analyze the structural system associated with San Miniato al Monte. The principal external loading that's applied to this building would be snow accumulating up here on the roof, along with a very substantial weight of the timber roof deck itself. What we're going to do now is follow the load path from that point of application, the roof surface, all the way down to the structural foundations. First, what supports that roof? Well, the best way to figure it out is to remove it and see what's there underneath supporting it. Well, we see, at first glance, you might think that the roof is supported by these trusses. But in practice, there's another structural element intermediate between the roof and the roof trusses, and that's these longitudinal beams that you see on tops of the trusses. It turns out that in a typical roof structure like this, the trusses are too far apart to adequately support the roof. And so we need some elements that are closer together to provide the first layer of support, if you will. And those are these longitudinal beams. They are beams, so they carry load in flexure, just as we saw in our lecture on beams. And they generate reactions out here at the ends in response to the transverse load associated with the weight of the roof deck and snow above them. Those reactions are transmitted to the trusses at the points of connection where the beams are actually attached to the trusses. So now let's remove these beams and focus our attention on those trusses. Remember that the trusses are loaded at concentrated points where the beams are physically attached to those trusses. And remember from our lecture on trusses, the trusses carry load essentially like beams as well. In this case, of course, they're made up of a framework of elements, and those elements are carrying load in compression and tension. But like a beam, a truss experiences compression on its top members or top chord and tension on the bottom members or bottom chords. And like a beam, the truss generates vertical reactions out at its ends, And those vertical reactions are transmitted to the structural system at the points of support, the connections, where the trusses are actually tied to the vertical walls. So now we can remove the trusses and follow that load path even farther down. At this point, we're almost ready to talk about these vertical walls, except let's pause for a moment and note that there's another wall on the structural system, the back wall that you see back here. Notice that the back wall is peaked and it follows exactly the same alignment as the roof trusses did. And so as you might guess, this back wall is participating in carrying the roof loads. It carries the same share of the roof load as any of those trusses that are running parallel to it. But it serves a much more important structural function. And to understand that function, we actually have to remove it, as we have with the other elements. So I'm going to start by removing a couple of connectors that tie it to the structural system. And at this point, we can lift it away along with the arch that supports it from underneath. And at this point, I would ask you to note that the sidewalls that remain are actually quite wobbly. They're now not too terribly stable from a structural perspective. And based on that, we can see what the principal purpose of that perpendicular wall was. It was to stabilize the sidewalls so they're better capable of serving their principal function of transmitting load vertically down through the structural system. Now we can take those walls away and look at what's underneath. As we'll discuss when we talk about the early Christian basilica form and early Romanesque churches, San Miniato al Monte actually has two aisles located out here beyond the central hallway or nave of the church. Of course, to access those aisles, we need openings through the walls, and those openings are provided for us by this succession of arches that run along the side walls. We know from our lecture on arches that arches carry load principally in compression, and in this case, that compressive force is used to channel the weight of the walls and everything above it around the openings and down into the structural columns. So there's the function of those arches, which we can now remove. Finally, all that's left are our 6 principal structural columns. The columns, of course, now pick up the load from everything that came from above and transmit it down into the structural foundations in direct axial compression. And I would ask you to remember that at each stage in this load path, each element was carrying not just its own weight, but the weight of every other element above it in the path. And so by that logic, you can recognize that this set of structural columns is actually carrying the entire weight of the building on its shoulders and transmitting that weight down to the foundations. And that is how a structural system works. And that general methodology that I just talked through is the process that we use to analyze and understand how structural systems work. We'll be revisiting this process a bit more rigorously in the second half of the lecture, but before we can do that, we need to address an all-important prerequisite for the study of load paths, the study of loads. Structural systems are heavily influenced by the loads they're designed to carry. Certain loads dominate the design of certain types of structures. For example, wind and earthquake loads dominate the design of skyscrapers. Snow load dominates the design of flat roof buildings in northern climates. But all structures must be designed to resist all relevant loads. And each different type of load may have its own distinct load path. For example, this structure here is called a braced frame. We'll be looking at it more closely in our lecture on iron-framed buildings. Now, when the weight of snow falls on the roof of this building, it would be carried principally by these roof beams up here. And the roof beams carry load in flexure, and they transmit their load out to the columns, and the structural columns transmit the load down into the foundations. This cross-bracing out here is stabilizing the frame, but it's really not significantly participating in the transmission of load from the roof down to the foundations, because the loading is principally vertical. On the other hand, if we now consider the load due to wind striking the side of the building, now those diagonal members, those bracing members, are decisively engaged in carrying those lateral loads. In fact, they're the most important elements in the lateral load path. And if you don't believe me, all we have to do is actually take those bracing members out and see that the braced frame, in the absence of bracing, could carry no lateral load whatsoever. So let's talk about loads. Back in lecture 2, we saw that there are 2 major categories of load: dead loads, which are permanent and unchanging, and live loads, which vary in both magnitude and location. There are many different types of live loads, but we're going to focus on the 5 most important ones: traffic loads, occupancy loads, and environmental loads due to wind, earthquakes, and snow. First, dead load, which includes the weight of the structure itself, plus any non-structural elements that are permanently attached to the structure. Now, in many structures, the dead load is very small in comparison with a live load. This is the roof system of my local building supply store. It's the place where I go to buy all the materials for these wacky demonstrations. And because the spans are short and the main structural elements are lightweight trusses, the self-weight of this system is likely to be less than about 10% of the weight of the snow that accumulates on the roof above in wintertime. By the way, if you're ever shopping in a building supply store and you need to get the attention of a sales clerk, try standing in the middle of an aisle and taking photos of the roof. I guarantee you'll draw a crowd. Now, unlike my building supply store, monumental structures like the Golden Gate Bridge tend to be dominated by dead load. The total weight of the Golden Gate Bridge, not including the cable anchorages and the approach spans, is about 840 million pounds, over 20 times larger than the total traffic load. In general terms, dead load is much more predictable than live load. Standard material property references tell us that steel weighs 490 pounds per cubic foot. Reinforced concrete is 150 pounds per cubic foot, and so on. There's very little variability or uncertainty in these numbers, so we can calculate the weight of structural components with a very high level of accuracy and confidence. Still, there is a significant challenge in designing a structure for dead load. At the start of the design process, the structural self-weight can't be calculated because the structure hasn't been designed yet. And so the dead load needs to be estimated initially and then checked and updated later in the process once the sizes of all the structural members have actually been determined. This process usually requires a couple of iterations because each update of the dead loads can change the required sizes of the members, which of course changes the dead load again. Now, this process is absolutely fundamental to structural design. My students know that they won't get a passing grade on their design projects if they don't do it right. And yet, this catastrophic collapse of the Quebec Bridge in 1907 was caused by the engineer's failure to properly calculate dead load in just this way. He estimated, but he didn't check. And 75 men died as a result. We'll revisit this tragic story in Lecture 17. Next, traffic loads, which include the weight of cars, trucks, trains, and any other vehicles that happen to be crossing a bridge. In the case of an elevated airport taxiway like this one, traffic loads can even be airplanes. Now, when the Golden Gate Bridge was designed in the late 1920s, it was engineered to carry traffic loads of 5,900 pounds per foot of span length. That equates to over 38 million pounds of traffic. Designing a structure for traffic load is challenging because so many aspects of the loading may change over time. Traffic volume tends to increase over time, as does the weight of trucks using our highways. Roadways are frequently resurfaced, and the weight of the additional asphalt or concrete also has to be accounted for. A sad example of this challenge can be seen in the 2007 collapse of the Interstate 35 bridge over the Mississippi River in Minneapolis. A major factor in this disaster was the combination of heavy rush hour traffic and the weight of construction materials that had been temporarily positioned on the bridge as part of a planned resurfacing. Next, occupancy loads. They include the weights of people, furniture, and movable equipment, typically in buildings and other kinds of public spaces. The equivalent for bridges is called a pedestrian load. And both occupancy and pedestrian loads are very difficult to predict because their functions, the functions of facilities, often change over time. And, well, sometimes people just behave in very unpredictable ways. For example, in 1987, a ceremony was held to commemorate the 50th anniversary of the completion of the Golden Gate Bridge. 50,000 people were expected to attend, but instead, 800,000 showed up. At one point, an estimated 300,000 people crowded onto the bridge itself, producing a total load roughly 15% larger than the maximum traffic loading that the bridge had been designed for. Fortunately, the structure was never really in any serious danger, because even at that maximum planned traffic loading, the main cables are actually only stressed to about 40% of their capacity. The factor of safety that's built into the design was more than enough to accommodate this accidental overload. Nonetheless, this incident clearly demonstrates the inherent challenge in designing for live loads in public spaces. Next, wind loading. The pressure exerted by wind striking a structure. Here we have a tall building, which are, as we've talked about, is particularly susceptible to having its design influenced by wind loading. And here we have a wind load. And it's pretty obvious that when we switch on the wind load, its principal effect is going to be to cause pressure on the windward face, the front face of the building, and that tendency will, there will be a tendency of the building to overturn as a result. Well, let's verify that hypothesis. I'm going to turn on the wind. And notice indeed that the pressure on the front face does indeed tend to cause the building to overturn. What you may not have noticed, though, in that demonstration was that pressure on the windward side is not the sole effect of wind loading. When the wind blows on a structure, it also circulates around the building and actually creates a vacuum on the backside or leeward side, the side that's away from the direction of the wind. That vacuum has the effect of causing suction on the backside, which further contributes to that tendency of the wind to overturn the structure. Watch carefully now as I turn the wind back on again, and watch for the facade of the building to actually pull out away from the structural frame as a result of that suction. And indeed, here you can see that facade slightly pulling away from the structural frame. Another very challenging aspect of wind load that has to be taken into account in design. Now, throughout history, the effects of wind loading have profoundly influenced structural design. The great Gothic cathedrals of the Middle Ages reached their ultimate structural limits as a result of wind loading, as we'll see when we discuss this cathedral, the Cathedral of Saint-Pierre at Beauvais in France. In 1879, the Firth of Tay Bridge in Great Britain, then the longest bridge in the world, collapsed because its designer didn't properly account for wind load. And in 1940, the collapse of the famous Tacoma Narrows Bridge, also known as Galloping Gertie, was only the most well-known of many wind-related suspension bridge failures. And finally, this New York City skyscraper, the Citicorp Tower, was seriously endangered by inadequate design for wind loads, as we'll see in Lecture 19. Next, snow load has a major influence on structural design in regions that experience significant amounts of snowfall in the wintertime. In these regions, the design snow load can be as high as 100 pounds per square foot of roof surface. And at that intensity of load, even a modest single-family home would have to be designed for upwards of 150,000 pounds of snow on its roof. Now, if you can't visualize 150,000 pounds of snow, imagine a fully loaded M1 Abrams tank sitting on the roof of a single-family home. That's a lot of snow. In 1978, the roof of the Hartford Civic Center in Connecticut collapsed catastrophically during a heavy snowstorm. As we'll see in Lecture 22, the main reason for this collapse was inadequate design of compression members in the roof trusses, but the event that triggered the disaster was an accumulation of snow on the roof, as you can see in this image. Earthquake loading has been the cause of many tragic structural failures throughout the ages. With the advent of modern tall buildings and long-span bridges, its importance today is greater than ever. Now, if I could clear my braced frame out of the way and replace it with a different type of structural element called a rigid frame, which is a bit better suited to demonstrating the effect of earthquake loads, it's important to recognize that what we call an earthquake loading is not really a force, but rather an acceleration. In an earthquake, the ground moves rapidly beneath a structure, something like this. The movement of the ground is primarily horizontal, though some earthquakes do have a bit of a vertical component. And when the ground moves rapidly, at first the building tries to stand still. Remember, a body at rest tends to remain at rest unless it's acted upon by an outside force. Once the ground has moved for some distance, the building has to follow along, which means it has to accelerate. Newton's second law tells us that force is equal to mass times acceleration. And so the mass of the building being accelerated laterally is exactly equivalent to a force. And that's why in designing structures to resist earthquakes, engineers represent the lateral motion of a building as the equivalent of a lateral force applied to the building structure. In the 1989 Loma Prieta earthquake in California, a section of the upper deck of the San Francisco-Oakland Bay Bridge collapsed onto the deck below. This collapse was caused by the longitudinal movement of the bridge supports during the seismic event. The pier moved, the bridge deck didn't follow along, and the unsupported end of the span fell, as you can see here. The nearby Golden Gate Bridge suffered no damage in this earthquake, but since the epicenter was over 50 miles away, and there was still a lot of concern that the bridge might not survive either a closer or a larger quake. As a result, a major retrofit of the bridge to increase its seismic resistance began in 1992, and it continues today. Now that we've examined the types of loads, let's look a little bit more rigorously at how load is actually transmitted through a structural system. And for the science we'll need to accomplish this purpose, let's turn once again to the great Sir Isaac Newton. Thus far in this course, we've seen two of Newton's three laws of motion, published in his Principia of 1687. The first law is the all-important principle of equilibrium. And we've just seen his second law as the basis for our understanding of earthquake loading. Now we turn to Newton's third law, which is every bit as important for our understanding of structures. Newton's third law says, for every action, there's an equal and opposite reaction. This principle might sound similar to the principle of equilibrium, but it applies more specifically to the point of contact between two bodies. If I push on this table with a force of 5 pounds, the table pushes back on me with an equal force of 5 pounds, but in the opposite direction. The application of Newton's third law occurs right here at the interface between my hand and the table, where that transmission of force is occurring. Similarly, we'll use Newton's third to understand what happens at the interfaces between the elements that compose a structural system. To illustrate this principle, I'd like to return to a great structure that we've already seen a number of times in our discussion of engineering mechanics. Daniel Badger's iron storage building at Watervliet Arsenal in New York, built in 1859. This is a great subject for our analysis of structural systems, not just because of its historic character, but also because the structural system is so beautifully configured, it's so easy to see, and by the way, it's also very well documented in the historical record. This 3D computer model shows the structural system of Watervliet in just about any orientation we'd like to look at it. Note that the exterior walls are all solid cast iron, and within these walls are a series of 15 parallel iron frames, spaced 12 feet apart. Now let's focus on a single frame. And as you can see, this frame includes two main interior columns and two exterior columns, which are actually built into the cast iron exterior walls, so they're called engaged columns. Up at the second floor level are two cast iron beams that support galleries on either side of the building, and on top is a roof system composed of 3 trusses supporting a series of lightweight roof beams, just like the ones we saw in the roof of San Miniato al Monte earlier in this lecture. The beams support the roof deck, which is made of iron sheeting. Now, as we saw earlier, to examine a structural system, we follow the load path from top to bottom. In this context, top means the place where the external loads are applied to the structure. The structure's principal external loads are snow on the roof, plus the occupancy load that occurs on that second floor gallery. Let's start with the roof. Here, the snow load is applied directly to the iron roof deck, which is directly supported on those roof beams shown here. Each beam spans 12 feet from truss to truss, and each carries its fair share of the snow load and the weight of iron roofing immediately above it, as well as its own weight. These 3 components of the loading are modeled as uniformly distributed loads on my free body diagram, and this total downward loading is then counterbalanced by upward reactions out at each end. I've labeled them as R for roof reactions. Based on the principle of equilibrium, each of these reactions then equals half of the total load applied to the beam. We could easily calculate this number, but we don't need to here. To understand the structural system, we only need to recognize that these reactions incorporate all of the dead and live loads associated with the roof. Now, these reactions occur at the connections between the roof beam and its supporting trusses at either end. So we can think of the reaction R as the force of the roof truss pushing upward on the beam to keep it in equilibrium. Now let's shift our focus from the roof beam to the main roof truss. The roof beams are attached to this truss at 14 points along its top member, which you'll recall we call the top chord. And here's where we'll use Newton's third law. For every action, there's an equal and opposite reaction. If the truss is pushing upward on each beam with its reaction R, then Newton's third law tells us that each beam is pushing downward on the truss with that same force. This downward force is applied at the point where the beam connects to the top chord of the truss. And since one beam frames into the truss from either side, the total downward force applied at each of these connections is 2 times R. These 14 forces plus the self-weight of the truss generate reactions at the ends of the truss, which I've designated as T for the truss reactions. And because the trusses are actually supported by columns, we should think of these two reactions as the upward forces applied by the columns to keep the trusses in equilibrium. And now let's look at that second load path, the one that originates with the occupancy loads on the second floor gallery. These loads are applied to a wooden floor, which in turn transmits load down to the iron floor beams. The floor beams carry load in essentially the same way as the roof beams. Each one carries its own self-weight, the weight of the wooden floor, and the occupancy load. These loads generate beam reactions, which I've designated as B on my free body diagram. And finally, we consider the columns. Since the top of each main column supports the ends of 2 different roof trusses, Newton's third law tells us that the column experiences a downward force associated with each of these reactions. I've shown it here as T1 plus T2 for the sum of the 2 truss reactions. Lower level of the column supports a beam, and so the reaction B is applied as a downward force at this point. These 2 downward forces plus the weight of the column itself generate the upward reaction C at the base of the column, and according to Newton's third law, this same reaction force is also the downward force applied by the column down into the building foundations. Now notice that 2 different load paths, one originating with the snow on the roof and one with the occupancy loads on the gallery, both merge together, sort of like a highway on-ramp in the lower part of this column. And in the Watervliet building, this merging of load paths is beautifully illustrated by the unique configuration of the column itself. It's called a Siamese column because the 2 parallel elements are connected together like Siamese twins. But they remain visually distinct, and so they do a wonderful job of communicating their respective load paths. The longer main column carrying the roof loads, and the shorter twin carrying the gallery loads. And by the way, that physical connection between the 2 columns is relatively light because the load is transmitted down through the columns on 2 parallel vertical paths. So the horizontal links between the columns really don't carry any significant force. So let's recap the structural system analysis we've just completed. We started by breaking a complex assembly of structural elements into its component parts. Then, working from the top of each load path, we constructed a free body diagram of the structural elements that directly support the building's principal loads. In this case, the roof beams and the floor beams. Then, based on Newton's third law, we took the upward reactions of these beams and we flipped them around and applied them as downward loads on the supporting structural elements. We continued this process step by step through successive elements from beams to trusses to columns to the foundation. And at each step, successively greater loads accumulated. The weight of each element was reflected in its reactions and then passed along to the elements below. Ultimately, those reactions at the bottom of the columns, the ones that were designated C on my free body diagram, incorporate the total weight of the building, plus any total external load. This cumulative chain of action and reaction is the load path. And as you can see, the load path is not some vague or theoretical concept. It's a real physical pathway that we can visually trace through the structure from top to bottom. Structural engineers often talk about the flow of forces through a structure. And indeed, it's helpful to visualize internal force as if it were water flowing through pipes, combining with other flows at pipe junctions, and finally emptying out into the earth beneath the foundations. If it works for you, use it. Our study of the scientific principles of engineering mechanics has now come to an end. But the best is yet to come. As Lord Kelvin once said, the life and soul of science is its practical application. Over the past 8 lectures, I've given you a taste of practical application to illustrate the power of those scientific principles that we've been talking about as tools for understanding structural elements and structural systems. But now we're entering the true life and soul of this course, 15 lectures in which we'll apply the principles more systematically in a series of thematic case studies of great buildings, bridges, and towers. And so it's time to leave the laboratory. It's time to leave these great experiments designed to demonstrate how the scientific principles of engineering mechanics work and head out into the built environment where the world's greatest structures are waiting for us. Next lecture, ancient structures from the pyramids to the Parthenon. Until then, thank you.